In this video, we're going to be taking a look at numbers 18 and 19 on the Gravity and Uniform Circular Motion review sheet. Number 18, you and a friend are sitting in class. The center of mass of you and the center of mass of your friend are 3.8 meters apart, which is why we have R equals 3.8 meters. We're going to find the mass of both you and your friend if your friend's mass, which is M1, is 1.5 times your mass, which is M2. So we're going to say M1 is your friend, M2 is you, and your friend is 1.5 times your mass. And we know, we're given that the force of gravity between the two of you is 2.45 times 10 to the negative 8th newtons, which is a very, very small number. So first, we're going to use Newton's law of universal gravitation. And the tricky part here is knowing that your friend's mass is 1.5 times your mass. So I'm going to plug in 1.5 M2 for your mass, because that would be then what your friend's mass is. So basically, I'm just plugging in this 1.5 M2 where M1 was. And now I can just simplify. 1.5 M2 times M2 becomes 1.5 M2 squared. And I just need to do a little algebra here in order to finish solving. I'm going to solve for M2, so I'm going to get this R squared out of the denominator and multiply it over, which is why I have force of gravity times R squared. And then this G and 1.5, I've got to divide out. So that's why they're in the denominator now. And then I got to get rid of the squared on the M2, so I take the square root. Plugging in my numbers, I put in the 2.45 times 10 to the negative 8th newtons for force of gravity, 3.8 meters for the distance between them. Don't forget to square it. In the bottom, the 1.5, and G, which is 6.67 times 10 to the negative 11th newton meters squared per kilogram squared. That is the same everywhere, so anytime you see G in one of your equations, you can just plug in the 6.67 times 10 to the negative 11th. Plugging that into my calculator, I find out that your mass is 59.5 kilograms, and your friend, since he's 1.5, or she's 1.5 times your mass, is 89.2 kilograms. Moving down to number 19. A satellite is in low Earth orbit and is 225,000 meters, or 225 kilometers, above the surface of the planet. How fast is this going, or what is the orbital velocity? A couple of numbers which we need to know, which are on your equation sheet and are also written on the board in class. The radius of the Earth is 6.371 times 10 to the 6th meters. The mass of the Earth is 5.972 times 10 to the 24th kilograms. In our equation, we're going to have an ms, which is the mass of the satellite. We're trying to find the orbital velocity, or how fast this thing is going, and here's my picture. There's the planet Earth, and there's the 225,000 meters. Now, in order to use any of my equations that I've got for satellite motion, I need to know how far apart the two objects are from their centers. So this 225,000 meters is just from the surface of the planet to the dashed line. I have to add in the radius of the planet in order to go from the center of the planet out to the satellite. So my total distance, or the total radius, is the radius of the Earth, 6.371 times 10 to the 6 meters, plus the distance above the surface, which is the 225,000 meters, giving me a total distance from the center of the planet, the actual orbital radius, of 6.596 times 10 to the 6 meters. Now, I know on your equation sheet, we have an equation for velocity for things that are orbiting. I just want to show you where it comes from. We know that gravity is the force that holds this satellite in orbit around the Earth. Gravity is given by Newton's law of universal gravitation, big G, mass of the Earth, mass of the satellite, over that distance between them squared. And for centripetal force, I'm going to use mv squared over r because I want the v. Now remember, the mass in this centripetal force part is the mass of the thing that's orbiting, which is the satellite. And notice mass of satellite in both sides of the equation, so they will cancel. I have an r in the bottom and another r in the bottom, so they will cancel. But over here I've got two r's because it's r squared, so that's why the squared goes away and gets rid of that r total. Solving for velocity, which is the only thing left over here, I got to get rid of the squared, so I take the square root of big G, mass of the Earth, over the total distance between the two objects, or the orbital radius. Plugging in my numbers, G is, as always, 6.67 times 10 to the negative 11th newton meters squared per kilogram squared. Mass of the Earth, 5.972 times 10 to the 24th kilograms. And the distance between them we solved for it is the radius of the Earth plus that 225,000 meters to give me 6.596 times 10 to the 6 meters. And I get a speed of 7,770 meters per second.